Well, good morning, everybody. A lot of faces I don't recognize, but I'm guessing if you're active in our discussion group and issue tracker, I'd like to meet you face to face. And feel free over the course of the next few days to talk to myself. Glenn Forney is here, Mr. Overholt, about various problems that you're having. There are a number of speakers over the next couple days who are going to be talking about some of the details of new developments in FDS. I've listed them here. What I want to focus on this morning is what we're doing currently in validation, and also I want to talk about pyrolysis modeling. Before I get started, is anyone in the audience an enforcement official, like a code enforcement official? One, two, a couple in the back. Okay, good. First presentation is for you. So the last time I spoke at this meeting, it was 3 years ago, and I was talking about an emphasis that we were placing on V&V, verification and validation. And just to remind you what those terms mean, verification means, and this is what we do a lot as developers, that we're checking the math, that we're comparing against analytical solutions. We're making sure that the equations that we're coding up in FDS are actually being solved properly. Validation is where we want to see to what extent do these equations actually represent the real world, fire, for example. How well does it represent the physics? So a lot of our work is validation that I'll talk about today. I've just got some snapshots of some experiments that we've looked at over the last couple of years. My role in doing V&V is to look at a lot of the work that's been done in the last 30 or 40 years. There's a tremendous amount of data out there conducted at labs throughout the world. The trouble is that this data is sometimes hard to find. You know how it goes. You know, you have a student that does some experiments, publishes a paper, graduates, gone. And I've had a hell of a time trying to track this stuff down. And for those of you here, I'll make the appeal one more time. If you're a graduate student, master's, PhD, or you work at a lab, and you've got some data that you think would be good for FDS validation, please contact us. Because so often I hear after the fact that, oh, we did these really nice experiments. And I'll say, oh, where's the data? Well, the student left, it's gone. So I'm really trying to capture a lot of the data. We have now in the FDS repository probably the most comprehensive database of fire test data anywhere. Because even at places like NIST, we do not do a good job of saving data. And I've still got in offices that are cleaned out, you know, literally reels of movies, different kinds of tape media. A lot of this stuff is being lost. We're trying to capture it. And this is just, you know, a sampling of different experiments that have been conducted over the years. This is some work that Kelly Opert and Dan Madrikowski did at Underwriters Laboratory a few years ago, where they looked at venting from roof vents. They did this for firefighting applications. This is some work done like 20 years ago by NIST. This is a hangar in, I don't remember whether this is Hawaii or Iceland, to look at, you know, fires in very large spaces. This is some work done at NIST a few years ago looking at extreme post-flashover conditions. This is some work that was done in New Zealand by a graduate student of Mike Spearpoint's named Roger Harrison. And what you find is, you know, Mike came to me a couple of years after this work was done, and he said, oh, I had some student who did this stuff. It might be useful to you. And then Roger and Mike helped me put this together. But it's a heck of a lot of work to get these data sets together. So again, if you are a student and you're doing this sort of thing, contact us early so that we can work with you to set up the data in a form that makes it easy for us to process the data. Chris Overholt, who will speak after me, is going to talk about a process that we have now of analyzing this data. And we literally, you know, every night we process data and create our manuals in what's known as continuous integration. These are just some other miscellaneous experiments that we've looked at over the years. United Technologies and VTT have done some work on mist suppression, so we've gotten some data from them. Jason Floyd worked with the National Fire Protection Research Foundation doing essentially telecom facilities and smoke detection with high air change rates. We've got some people at NIST doing wind engineering. You can't really read this, but a colleague of ours at FAA is doing some work with smoke movement cargo hold. So there's a whole bunch of different things going on in different parts of the world, special applications. And what we're really trying to do is we're trying to gather up this data and expand the database of FDS applications, because we envision in the next 10 years that when practicing fire protection engineers take a potential design to an authority having jurisdiction, we want that authority having jurisdiction to ask, what's the basis of the validation for this work? You know, can you show me an experiment that shows FDS works well for this application? And the workhorse of that is in our validation guide. You'll see charts like this. And my goal is to increase the number of data sets that we look at and the number of points and the range of validity. If you look at this, we call this ceiling jet temperature, but really what this is temperatures in compartments usually made near the ceiling, but not necessarily exactly in the ceiling jet. You'll notice that we now go from 0 to 1,500 degrees Celsius. When you're up at 1,500 degrees Celsius in a compartment fire, that's pretty hot. And so now if someone asks, well, how good is FDS at predicting, you know, X, Y, or Z, we show them these kinds of plots. The black lines represent the experimental uncertainty. The red lines represent, in some sense, the model uncertainty. Did I jump over a slide? Yeah, I jumped over a slide. And we put together a very simple way of expressing the model uncertainty. And I've gotten a little grief from people saying, well, I don't remember this statistics. I took that 20 years ago. But the best way to think about this is, remember when you were in high school and the teacher said he was grading on the curve, right? And you got a 65 on an exam and the mean was 55. And so, you know, the grades were shifted based on if you were 1 standard deviation or 2 standard deviations above the mean. In a similar way, that's how we're expressing our model uncertainty. So, for example, if a model predicts, if you take a FDS and you predict a temperature of 300 for whatever, and you know that the model has a particular bias, that is, it tends to overpredict or underpredict by 5%, 10%, whatnot, we have in the validation guide a very simple method of expressing the uncertainty of that calculation. And I think that's very important when you present results to an authority, is not just to say, FDS predicted 300, 300 is less than 350, therefore, we're good. You want to be able to express that with the uncertainty of the calculation in mind. With the help of Chris Overholt, we now, when we process all this validation data, and in the last few years we have about 800 to 900 individual experiments, I'd say about 5,000 individual points. And in the validation guide, in the back, we list all the different quantities that we are predicting in these experiments, a reference to where in the guide we discuss it, the number of data sets that we have, the number of individual experiments, and the model bias and the standard deviation, and also the experimental uncertainty. When we talk to people who want to do new validation work, we say, take a look at this chart, and if you see for ceiling jet temperature 11 data sets and 552 points, okay, that's where we think we have some pretty decent coverage. Go down the list, though, and you see for a lot of these quantities, and these are quantities that people use FDS to predict. You know, we have 1 data set, 2 data sets, one or two data sets. We'd like to, in the coming years, continue to increase the number of data sets, the number of experimental points to add more validity to our calculations. A lot of this work has been driven by the U.S. Nuclear Regulatory Commission. They are a big supporter of ours, and I do a lot of work with them. Where did they go? That's the next slide, I'm sorry. You see here that we just got through our second round of a V&V exercise with them. So you can think of the verification and validation work we do with US NRC is a subset of our more comprehensive validation guide for FDS. A lot of people are confused by what validation actually means. Well, is the model validated or is it not? Well, it really depends. It depends on what the application is. So the NRC comes to us along with EPRI, the Electric Power Research Institute, and they say, we see that your models, FDS and CFAST, are being used by licensees to do fire PRA, probabilistic risk assessments. We need to know how accurate those models are. So they select experiments that are closely aligned with fire scenarios that they expect to see in plants. And they want to know for those types of applications how good the model is. And we have a similar chart to the one I showed, but not only for FDS, but for CFAST. There's a zone model that's developed in France called MAGIC, and then the empirical correlations. This is something new. We've actually gone back in time 30 or 40 years, and we're now including the empirical correlations in our V&V exercise. Because believe it or not, a lot of people, you read through something like the SFP handbook, and you see correlations like the Heskestead, plume correlation, or the MQH compartment temperature correlation. And everybody just assumes that those are, based on experiment, and they're right in some sense. They're accurate. But how accurate are they? Well, we're now, V&Ving those models along with the zone and the CFD models. Because what we've noticed is that, in practice, certainly in the nuclear industry and out, you don't just necessarily use FDS for everything. Sometimes you'll use zone models. Sometimes you use these empirical correlations. It depends on the job. And we want to be able to express the uncertainty of all these models in a consistent way. So the NRC has really helped us in that regard. Another emphasis is, if you look in the validation guide, we're trying to expand the range of our experiments. So if you look here, these are all the different experiments that we've looked at. And here's the heat release rates, fire diameters, sealing heights, and a number of non-dimensional quantities. I discussed this at the last meeting, but basically for a given fire scenario, you can express things like the fire Froude number, or Q star, the equivalence ratio, whether the fire is underventilated or overventilated, the ratio of the compartment's length to height. These are all non-dimensional quantities that kind of characterize the fire scenario. And our goal in doing V&V is to expand that range. Because if you're an authority having jurisdiction and someone comes to you and they're modeling, I don't know, some crazy, huge facility, you might say, well, wait a second, is the model appropriate for this? And you can look at these non-dimensional quantities and decide whether or not it is. Okay, so a lot of the work we've done in V&V is focusing on gas phase quantities. But we still, surprisingly, are somewhat far behind in actually modeling the actual burning of stuff, or pyrolysis. Now, for many of you who do fire protection engineering design, pyrolysis isn't all that important, right? Because usually you're dealing with some kind of specified fire, right? If you were analyzing this hotel, and let's say it had a lobby with some unusual geometry, the authority having jurisdiction would probably give you a heat release rate for, you know, the restaurant if it were to flash over. And you just dial that heat release rate into your model, and then you predict temperatures and smoke concentrations and what have you. So there hasn't been as much driving us into pyrolysis as you might think. I mean, as a fire modeler, I'd like to be able to model fire, including the actual burning of stuff, but a lot of what our users are driving is the gas phase for specified fires. But we still are interested in doing pyrolysis. So I thought what I would do today is just kind of give you a brief history of pyrolysis modeling and try to give you an idea of where we're going with it. So when I started at NIST in 1991, I worked with Howard Baum and Takashi Kashiwagi. And those of you who have been around a long time will probably recognize those names. And there was a big effort at the time to study fire in outer space, because space shuttle was in operation, the space station was being built, and there was a big effort on NASA's part to study all sorts of science in space, fire being one of them, because not only was it interesting to study fire phenomena, but also there was concern about, you know, if you have fire on board a spacecraft, what would happen? So we worked with someone at NASA, Glenn, named Sandy Olson, who was doing experiments. And one of the experiments she did was to just take a piece of tissue paper called a Kim wipe, ignite it, and then watch the flame spread. And in a zero gravity environment, the flame spread is it's like a donut expanding out from the ignition point. And that's nice because from a modeling point of view, it's like a very nice, simple laminar flame. So Takashi and some of his co-workers from Japan developed a model, and that model consisted of a description of the Kim wipe that had 3 reactions when it heated up. It was a first stage is you eject fuel, then char forms, and then the char oxidizes. Along with the 3 reactions, there are, you know, about a dozen measurements that need to be made of things like K, rho, and C, thermal conductivity, specific heat, density, and kinetic constants. And these kinetic constants are measured with things known as TGA, thermogravimetric analysis, DSC, MCC. There's a series of bench scale tests. Chris Lautenberger was supposed to be here, and that's the sort of thing he does with G-Pyro. But nevertheless, we had, in 1991, a fairly comprehensive description of the pyrolysis of this piece of tissue paper. Trouble is that it really was appropriate for small scale, like direct numerical simulations. We were very quickly pushed into a completely different area looking at rack storage fires because we happened to be working with the Research Foundation, the National Fire Protection Research Foundation, on a project to look at the effectiveness of sprinklers, vents, and draft curtains in big box retail facilities. And so we started developing what would eventually become FDS to look at these kinds of big fires. And with these kinds of things, we couldn't use that simple first principles type of pyrolysis model that we use for microgravity. Here, for this application, in order to predict the spread of fire on these boxes, what we would literally do is just measure K and rho and C for the boxes, the basic thermal properties. And when the boxes heat up to a certain, I'll call it ignition temperature, the boxes burn at a specified rate. And that specified rate you get from, you know, a measurement, like a cone calorimeter measurement, or something even larger, like when we burn a couple of boxes at a time. I had thought that this was kind of a placeholder pyrolysis model, something that we would eventually replace with the more fundamental model that we use for the microgravity applications. Sad to say, this really has not been replaced. This is still the workhorse pyrolysis model. For anyone who's doing it, this is what we typically recommend, because getting these fundamental properties through TGA and MCC is difficult. Now, I'll talk about that in a little while. And here you see I pulled out a slide when I was preparing this talk. I pulled out a slide from the year 2000 at a meeting of the NFPA Fire Suppression and Detection meeting in Orlando. I made the prediction in 2000 that we would soon have a database, a collection of sprinkler and material properties for all sorts of different things. That again has really not turned out to be true. We get calls all the time, posts on the discussion group. Hey, I got such and such a sprinkler. I mean, look up, there's a sprinkler in this room, I'm sure. What are the properties of this? We don't know. What are the properties of the carpet and the chairs that you're sitting on? We don't know. We can give you some suggestions as to how to measure them, but even then, we can't tell you exactly what to measure. So we really have not come as far along in developing this database as I had hoped. But the applications just keep coming, even though we were a bit disappointed with the progress in pyrolysis models. So we continued doing work with the simple K-rho-C ignition temperature specified burning rate model. And we started getting into forensics. One of our first applications was a fire that occurred down in DC in 1999, known as the Cherry Road Fire, in which 3 firefighters died at the top of a stairway due to a fire that flashed over in a basement. This was done with FDS-1. You can see SmokeView 1.0.1a there. And by the way, a little bit of FDS trivia. That default color that you see in that picture, Glenn Forney chose that color to match the boxes of that previous application, the box burning application, and that still remains our default color. Then, the next thing we were moved into was the World Trade Center investigation. And let me see if I can make this go. There we go. Make it work. All right. So when we started doing the World Trade Center investigation, we were confronted with, typical office furnishings, desks, chairs, computers, paper, and so forth. So we did a lot of cone calorimeter work, but we still used this same kind of pyrolysis model. We got the basic K, rho, and C. We assigned an ignition temperature, and we were able to model the spread of a fire through a building reasonably well, but not to the point of making a prediction. Okay? What we had to do is burn some of these workstations at full scale, calibrate our model, and then apply it to the whole building. That's less than satisfactory, but that's what we had at the time. In the meantime, we've developed some special pyrolysis models. Ruddy Mell has done work with the U.S. Forest Service predicting fire spread through vegetation, and we have a very special model for that. Anna Matala at VTT, as part of her PhD thesis, developed a model of electrical cable burning in which she used, you can see here a rendering from SmokeView, and we have essentially little thermal elements that are cylindrically shaped and they burn at a specified rate. Simo Hostika at VTT has continually improved our solid phase model, and he's built into FDS all the mechanisms that we need to do the pyrolysis the way we used to do it in that microgravity application. But what we're finding, the problem is getting the data. See this little device here is a TGA-DSC combination. It's a standard test apparatus, but it's very difficult. Well, it's not difficult to run if it's working and if you have people who know what they're doing. But what we're finding is that very difficult to get these fundamental properties for example, everything in this room if you wanted to model fire spread in here. I've worked in recent years with Stas Stoliarov, who was at FAA and now he's at Maryland, for just something like PVC, this is the number of properties that you need if you want to model the PVC combustion or pyrolysis using sort of first principles, where you're looking at the kinetics, you're looking at the details of the thermal conduction into the solid. This is still, we're still kind of stuck at the simple PMMA plastics. We have yet to take this methodology and simplify it to the point where you could take a piece of carpet or piece of chair, go to a standard testing lab, make these measurements, and then put them in the model. At the moment, I like to say that this is a PhD thesis. That's just not practical. A lot of good work's been done, but we're still not at the point where you can just go to a testing lab, get these properties, and plug them into something like FDS. I'm done. I'm done. So, and I list here, and you can read for yourself. I pretty much pointed out, these are the kinds of problems that we're facing in terms of pyrolysis. And I want you to look at number 5. I think part of the problem is that what's driving pyrolysis now, in my opinion, is forensic analysis. But the trouble is that the people who do forensic analysis, they're all kind of working, I wouldn't say secretly, but I don't hear from them very often. So I don't know exactly what kind of techniques are being used, whether the pyrolysis model in FDS is working or not. I'm just not hearing a lot about it. I hear more from the fire protection engineers who are doing design work, but they're not looking for the detailed pyrolysis models. They're just specifying the fire. So I'd be curious to talk to some of you this week, those of you who have been interested in pyrolysis, to give me some feedback about what's working and what's not working. So I'll stop there and take questions if you have them.
Just one question, I think. Keep things on track.
We're on track.